In this video, I'm going to discuss nuclear magnetic resonance spectroscopy. NMR spectroscopy is often described in organic chemistry textbooks in a very dry and difficult to understand way. In this video, I'd like to bring NMR to life and make it more approachable. NMR spectroscopy is a versatile analytical technique that is used to elucidate the structure of chemical compounds. Sample sizes of 50 milligrams or less can be analyzed in a non-destructive way. Before the widespread use of NMR, chemical compounds underwent chemical tests to help determine their structure. Chemical tests such as the Tollens test, the 2,4-DNP test, or the iodoform test were used to detect functional groups inside chemical compounds. Unfortunately, during the process of this analysis, the sample was destroyed because it undergoes a chemical reaction and cannot be recovered. By contrast, in NMR spectroscopy, after analysis is complete, the sample can be recovered and used for other purposes. This is particularly important in cases where there is very little sample available or the sample itself is prohibitively expensive to purchase. In the biological sciences, elucidation of protein structures often begins with NMR analysis. Even after spending weeks, months, or longer as an NMR sample, the pure protein can be recovered and used for other purposes. More routinely, organic chemists working in research laboratories often use NMR as a quick check of reaction products or the progress of their reactions. In the remainder of this video, I would like to show you a spectrometer that has been taken apart so that you can see inside. And lastly, I will use a live working spectrometer to obtain the spectrum of a prepared sample and show you how it's analyzed. Before we actually look at the spectrometer, there are a few key points of theory we need to keep in mind. First, the sample is placed into a magnetic field. The magnetic field aligns the spins of the nuclei. It can align them in two different ways. It can go with magnetic field, and that's the lower spin state of alpha, or they can align against the magnetic field, and that's the higher energy spin state of beta. The strength of the magnetic field determines how far apart these energy levels are split. The stronger the magnetic field, the further that they're split. For high resolution NMR, we require very strong magnetic fields, and so we use superconducting magnets. Because we are using superconducting magnets, they must be kept very cold. Once the sample is in the magnetic field, it can be irradiated with RF radiation, and this causes the alpha spin state to excite to the beta spin state. After the pulse is over, the nuclei which have been excited into the beta state relax back to the lower energy state of the alpha. This is detected by the NMR instrument as the time it takes the nuclei to relax back. This is then transformed through a mathematical formula into our readable spectrum. Now let's take a look at the actual instrument. Now let's have a look at how the instrument actually works. Here is our prepared NMR sample. This is usually 3 to 50 milligrams of sample dissolved in 1 milliliter of a deuterated solvent. The sample is placed inside the spinner like this. We'll have a look at this again in just a moment. At the heart of the NMR spectrometer is the superconducting magnet. The superconducting magnet is kept in the liquid helium chamber, which is kept at 4.2 Kelvin. Superconducting magnets only superconduct at very low temperatures, so we must maintain liquid helium inside this chamber and covering the magnet. Because liquid helium is so very cold, it must be kept isolated from the outside environment or it would evaporate very quickly. To help do this, there are 2 layers of vacuum at the bottom. Between these 2 layers of vacuum, there is a protective layer of liquid nitrogen, which is at 77 Kelvin. This liquid nitrogen helps slow the rate of evaporation of the liquid helium by helping prevent heat from transferring in from outside. After the liquid nitrogen chamber, there is 2 more layers of vacuum. The liquid helium and the liquid nitrogen must be refilled periodically. Now we'll take a look at how the sample goes into the spectrometer and sits in the probe. Now we have our NMR sample prepared and it's positioned inside the spinner. Now we need to put it into the spectrometer for analysis. The sample enters and exits the spectrometer here on top through this hole. The sample floats into and out of the spectrometer on a cushion of air. As the sample travels down the tube, it goes into the magnetic field and sits on top of a probe, which is where the data is collected. Now let's have a look at the probe. This is our probe, and it sits down in the magnet right about here. The sample then travels down the tube and sits into the probe just like this. We need to homogenize the magnetic field across the sample. So we spin the sample much like this, except it's done more smoothly in real life. And so it spins. The pulse of radio frequency radiation is transmitted here, and it's also received here. Different nucleus have different resonant frequencies, and so the probe must be tuned to the different resonant frequencies. It's exactly analogous to tuning in a radio station in your car on a radio. And so the probe detects the resonance, and this data is then collected by the computer and is transformed into the spectrum. Now let's take a look at our live spectrometer and run the spectrum, collect data on our sample. So now we have our sample. It's in the spinner. Let's put it in the spectrometer so it can collect some data. Now remember I said that the sample floats in and floats out on a cushion of air, so you'll get to see that here. Now let's start our experiment. Once the experiment is started, inside the spectrometer, the probe will tune to the specific frequency of the nucleus of interest and ensure the magnetic field is held constant and homogeneous through locking and shimming. This is what the lock signal looks like. The pulse sequence consists of 3 segments: a delay period for all nuclei to align to the magnetic field, a short pulse of irradiation to excite the spin states, and a few seconds to measure and record the relaxation of spins. The sequence is repeated several times to improve the signal-to-noise ratio. For example, in this spectrum was collected with 1 scan. Compared to this spectrum, which was collected with 64 scans, you can see that the baseline is considerably smooth. The more number of scans that are recorded, the better the signal-to-noise ratio will be and the smoother the baseline. This is the actual data the instrument acquires. This plot shows the free induction decay, or FID, of the excited spin state with time. This FID contains all the frequencies that will be a part of our spectrum after mathematical treatment. Let us now convert the FID into a readable spectrum using a Fourier transform function. After a few cosmetic adjustments, we are ready to reference the frequency scale to the internal standard of trimethylsilane at 0 ppm. The size of each signal is proportional to the number of magnetically equivalent nuclei producing the signal. With the integration software, we are able to calculate the area under each signal and correlate that to the number of protons that is creating that signal. This is a sample of ethanol. The spectrum shows 1 quartet for the 3 hydrogens on the methyl group, a triplet for the methylene unit, and a singlet for the hydroxy group.